computational mathematics. So we're just moving on the educational side. That we're signing on to.
I just read the last sentence. Is that what you were reading? Is that what you were laughing at, Floyd? What were you laughing at?
I was laughing at fractionally challenged. That's just the first thing that I saw.
Oh, I read the last sentence. That's what.
No.
I'm recording this.
Yeah.
Oh, okay.
Fine. So yes, imaginary complex numbers should be referred to as reality challenged, and rational numbers should be referred to as fractionally challenged.
Cool. Let's do it.
This is like.
Oh, and actually, I will send you this later. I have something I'm handing out to the class. Okay.
Email?
Huh?
I've seen this ASCM
Oh, okay.
thing in my
So,
email.
So yes, this is today's attempted April Fool's joke.
Oh.
Oh!
That's right. That's today.
Yeah, I've been pretty disappointed in April Fool's so far, but the day is not over.
But here's the actual funny part of this. I did this in cahoots with my friend and colleague Margot Gerritsen at Stanford. So she distributed this to her vector calculus class, and actually got a lot of signatures.
That's California, man.
Yeah. So.
Those people like.
Just be like, all right, yeah, let's
Those
Okay,
people.
So at least I can tell her that somebody would have.
I thought I didn't know if you were like handing this out and being like, "Hey, I found this online. What do you think about it?" I was like, "What is this for?"
Yeah, I thought it was a joke that you saw online.
Yeah, that's what I thought. It was a joke you saw online, and I'm like,
See, you need to come out more serious and be like, I
Yeah.
need you guys to sign this. This is really important.
"That's the problem. You don't have
I really tried.
you don't have a straight
You
face."
had to
I know.
commit to it, man. You had to
I
commit.
know.
Yeah.
I'm really
tried
bad
to-
at-
In fact, it was difficult to keep a straight face.
Especially with us, like.
Yeah, that's a big part because I mean her class is like really large, and also she's really assertive. So I'm sure her delivery was just great. But
I mean, if she said something like that and I was in the class,
I mean, I make you laugh by looking at you funny, so.
Yeah. So actually, I'll send you that later. So that maybe something that you might find amusing.
I'm gonna start calling them that.
Maybe you could use that. What?
You should do that in your college algebra. You should do
No.
that in your college algebra
I
class
don't
and
want
see
to
what
confuse
happens.
those poor kids even more.
Yeah.
Yeah.
Yeah. Too bad I didn't have this earlier.
Yeah.
Now you gotta wait till next year.
I could talk about yeah.
Fractionally challenged number.
Yeah. So, okay. Now, I want to briefly discuss a little bit about
I should post a copy of this.
some
about
material
it.
related to homework 3, since I believe. Shoot. Oh, I was using. Okay. I'm not sure which marker was mine. Well, it's one at work.
Nope. Why don't y'all throw away the ones that don't work?
I don't have one that works.
Instead of just leave them up there.
I just use
It's like, I don't
It's the marker graveyard.
especially all the ones without caps on them. I mean, it's like,
bag of markers.
I wonder if this works. Even if it doesn't have a
I
cap.
went through 5 markers in the last class.
So,
You're never going to get anything done today. You just aren't.
that's okay. No, because I'm not sure if I have a full slate of material anyway.
Let's just go home, man.
See?
I do have stuff to cover.
We're trying so hard.
Okay. So for homework 3, I want to give you a little background material that will hopefully make these problems a little more manageable. So about eigenvalue related decompositions. Okay. is related to first problem. So I mentioned this stuff quite a while ago, but you guys have plenty of opportunity to forget. So two matrices are similar, and in this context, similar means they have the same eigenvalues. Actually, I need to name these matrices. Two matrices A and B are similar if they have this kind of relationship. A is equal to P, B, P inverse, which is equivalent to B is equal to P inverse AP. So you can rearrange one to get the other. If this relationship holds for some invertible matrix P. So, so problem one, you're given that two matrices have a relationship like this, so you can use that to conclude that they have the same eigenvalues. Okay. The second point I want to make relates to problem number 3. Problem number 3 deals with a symmetric matrix. So if A is symmetric, so A is equal to A transpose. Okay. Then one thing we know about it is that A can be written this way as Q B Q transpose, so it has this kind of eigenvalue eigenvector decomposition. So Q has this form. It has columns Q1, Q2, Qn, and these are the eigenvectors. And Q is an orthogonal matrix, so Q transpose Q is the identity. D is a diagonal matrix that has the eigenvalues along the diagonal. So any symmetric matrix has this kind of decomposition. So that's one thing that is useful in this problem. And in particular, the matrix given in a problem is said to be singular. So singular meaning not invertible. So let's see, actually, yeah, I'll need to go to the next different board for this. Alright, so hopefully this will work as far as filming goes. Alright. So this line is still good?
Yes.
Okay. So if A is singular, so it is not invertible, and it has at least one eigenvalue that is equal to 0, possibly more than 1. So what that means is, if we look at the eigenvalues, lambda 1, lambda 2, up to lambda r, and then r plus 1, and so on up to lambda n. Let's suppose that all of these guys, these eigenvalues are equal to 0. And r is equal to the rank of A. So that's the dimension of matrix column space. What we can also conclude is that the first R eigenvectors these form a basis for the range of A. And then all the other eigenvectors, QR plus 1 up to Qn, are a basis. Also, both of these bases are orthonormal. For the null space of A, that's also known as the kernel of A. The set of all vectors, so that if you multiply them by A, you get 0. Now, all of this is from the discussion in chapter 2 about the singular value decomposition. All this comes from there. So it might be helpful to go back and review that. But what happens in this case, because the matrix is symmetric, is you always have this, A is U sigma V transpose, but if A is symmetric, that means that U equals V. So that causes some things to simplify. Okay, so when you're looking at problem 3 in homework 3 about iterative methods applied to a singular matrix, keeping in mind that a symmetric matrix has this kind of decomposition where it can describe, okay, here's the null space, then the rest of the vector spaces for range. That can help you figure out what happens in this kind of situation using an iterative method on a singular matrix. Okay. So hopefully all of this will make more sense when you go to look at that problem. Hey now, you're an expert on this already. But seriously though, I would also recommend looking at the material from chapter 2, chapter 2, related to eigenvalues and eigenvectors. There's one section on that, and then there's also a section on the singular value decomposition. Just keeping in mind that in this situation, U equals V. Okay, so yeah, you still have quite a while to do homework 3, and you might look at it and think, oh, there are only 3 problems. They're kind of hard. So,
That's mean.
Well, actually, the second problem has a significant MATLAB or Octave, whichever one you're using, significant programming component. So for problem 2, look at section 5.2 in the notes, the new section 5.2. So if you downloaded the notes at the beginning of the semester, you got to look at it again. So I wrote that up like a week or 2 ago. All right, so hopefully that helps you guys get the ball rolling.